Thank you. It's my pleasure to introduce the moderator of this session, Dr. Mike Barratt. He also moderated the last session, so you may have heard from him. But if you just joined us, let me say a few words about him. He has his bachelor's of science in zoology from the University of Washington, also one of my alma maters, his doctor of medicine from Northwestern, and he is board certified in internal and aerospace medicine. He arrived at the Johnson Space Center in 1991 as a project physician with Krug Life Sciences. And in 1992, he was assigned as a NASA flight surgeon, a very important position for all of us who fly, working in space shuttle medical operations. I first met Mike when he was assigned in 1994 to support our first crew in Russia for the joint mission between the shuttle and the Mir. I was on the backup crew, and he was my flight surgeon. We conducted that mission in 1995. From 95 to 98, he served as the medical operations lead for the International Space Station, and he was the lead crew flight surgeon for the first crew. He was selected as an astronaut in 2000, flew 2 space flights, one in 2009. He is the flight engineer for Expedition 1920. This marked the transition from 3 crew members to 6 permanent International Space Station crew members. He also conducted 2 spacewalks. He flew on STS-133. And then from 2012 through 2013, he was the manager of the Human Research Program at the NASA Johnson Space Center. He worked on payload science for the International Space Station, has been extensively involved in the medical and human factors applications for new space vehicles. As of 2018, he's been involved with human missions to Mars and dealing with the health risks of the spaceflight to Mars, especially from cosmic radiation. He's a particular interest in human adaptation to spaceflight, and he serves as the associate editor for space medicine for the journal Aerospace Medicine and Human Performance. And he's a senior editor of a textbook on the principles of clinical medicine for spaceflight, now in its 2nd edition. Mike continues as an active astronaut and serves as a lead medical representative for the astronaut office. So with that, Mike, please proceed.
All right. Thanks very much, Bonnie. I get the only good thing about an intro like that is it reminds me how much fun I've had at NASA. It's been an amazing career because the work is really exciting. So I really appreciate those words. We're going to dive right in. We have a somewhat short time block here, 7 speakers, so I'm going to be very brief. But I'll just start by noting that if a lot of people fly in space, they generate a lot of information. And that helps us inform the human response to spaceflight. But that's only true if it's done in a thoughtful and methodical fashion. So this panel is entitled Lifetime Surveillance, and I'm taking a bit of license personally to view that as a complete channel that includes a data feed, including the collection of this information, the curation of that data, the ongoing analysis, the translation of that into identification of health outcomes, and if needed, treatment of spaceflight-related occupational disorders if warranted. So let's go right to our panel members, and we'll be at pretty much every end of that channel. We'll start with Dr. Ronak Shah. Very briefly, if you could use the word steely-eyed clinic director, that would be Dr. Shah, for those that know him. Dr. Shah is boarded in internal and aerospace medicine and serves as the medical director of the flight medicine clinic at the NASA Johnson Space Center. His job includes oversight of clinical operations for the astronaut office and the JSC workforce, both here in Houston and overseas in Russia. He has had experience in the Human Research Program, the Exploration Medical Care Capability branch. He's overseen operations in the Neutral Buoyancy Lab in Star City, Russia, and has been our medical director since 2017. We've challenged him with lots of things like pandemics and travel, and Dr. Shah continues to manage these things brilliantly. Sadly, Dr. Shah will be leaving NASA to join the UTMB faculty as their new director of the Aerospace Medicine Division. So unfortunately, he's leaving a big Ronak Shah-shaped hole in the flight medicine clinic. However, we are really excited to have him in this new position, and we know we'll be working with him closely in the space medicine community. And I've asked Dr. Shah to talk a little bit about the status of the TREAT program, implementation and experience so far. And I'll let Dr. Shah explain what that is and define it for us. So go ahead, Ronak.
Well, good morning, good afternoon, good evening to all of our viewers. Certainly appreciate all of you dialing in. And Mike, thank you very much for that kind introduction. So diving right into this, I was asked to speak about the TREAT Act, and that is to research, evaluate, assess, and treat astronauts act, as we refer to as the TREAT Act. And it was signed into law by our president in 2017 after almost a decade's worth of effort by different members of our NASA family across the country. And in short, what it does is it authorizes NASA to screen for, to diagnose, and to treat both medical and psychological conditions that are associated with spaceflight. And signing the TREAT Act into law was seen as a huge victory related to the health and wellness of the crew. Now, since then, since 2017, various steps have been accomplished in the pathway of implementing the TREAT Act, including, for example, a workflow for the crew to follow if they wish to file a claim, in-house support with our own clinic staff. We have an improved relationship with the Department of Labor, who handles workers' compensation cases for civilian federal employees. And these terms will come together in just a moment. But as a quick background, we know that our astronaut population faces occupational exposures during all phases of their career, from terrestrial training to launch and landing, and all of the on-orbit activities in between. And we are very, very rigorous in our approach to screening and monitoring. And the LSAH program, the Lifetime Surveillance of Astronaut Health program, enables continuation of this screening and monitoring beyond the individual's active astronaut career. And so when an event arises, it is important to keep in mind the difference between acute injury versus that which is chronic, which plays into how we operate. And for a crew member who has a concern, they can initiate a conversation with either me or their flight surgeon in the clinic. We will gather all of the pertinent medical information and submit that to the Department of Labor for evaluation. Now, this has the flair, everything I'm saying so far has the flair of a traditional workers' compensation case. What's worth noting is we worked very closely with the Department of Labor to have our cases sent to a special team that handles unique situations. And a team of us went up there to educate the actual people who will be reviewing these cases on some of these challenges with spaceflight, exposures during training, in-flight, launches and landings, so that they have a much more global understanding of the occupational exposures that our patient population is exposed to. Now, where the difference comes in for us is the Department of Labor generally is the group that renders a position on this, meaning they determine if there's an association between the occupational exposure and the medical outcome. What the TREAT Act has done is added in an additional step there, and that is if there is no evident association between the exposure and the outcome, the case can now be reviewed internally one more time. And this is the difference that we have gained as of the TREAT Act. The opportunity for an internal tab, which is the TREAT Astronaut Act Board, again, tab, to review the case. And we have a membership that is comprised of our chief medical officer as the chair, myself, and 3 other physicians. And what we will do is we will bring in expert consultants like members of the LSAH team or others as needed to help provide guidance. And the goal here is to ensure a thoroughness in our assessment, and then allow for the chief medical officer to pull together a consensus statement that will then be passed on to the chief health and medical officer at NASA headquarters, who is the delegated authority from the NASA administrator. In the end here, the goal is to levy a position on how NASA stands on this particular condition. So one of the things I do like to make note of is the phrase 47 plus 20 equals 67, some arithmetic. And right, roughly speaking, the average age of a crew member flown on ISS is about 47 years of age. The ISS has been in operation for just over 20 years. What this means is 47 plus 20, 67. And what this means is we will begin to see a wave of our astronaut population entering their 70s. And as we look ahead, the challenge we will face as individuals transition from their 70s into their 80s and so forth is determining that separating line, that position of what disease do we see that is secondary to occupational exposure versus that which is secondary to the natural process of aging. And so that to me is why we're working really hard to build a solid foundation for the implementation of the TREAT Act today so that decades worth of astronauts in the years to come will be able to gain. So with that, Mike, and that brief introduction to the TREAT Act, I'll turn it back to you to go to the next one.
Okay, very good. And thanks for keeping whack on time. I will just ask you one question is, how will you publicize your findings if you decide in this board that a particular health outcome is attributable to spaceflight? Will we make that public, knowing that that may be precedent setting for a very large industry?
The intent would be to share that information internally with NASA, absolutely. How that is publicized up and out is still TBD, whether that is done in the form of a newsletter, research announcement, etc. One of the challenges that we must keep in mind is balancing what we learn while protecting the privacy of the individual. So I think that can be done. And I also am an advocate of sharing information as we learn it for the betterment of the community. So again, internally, to answer your question, is once a position is levied by the administrator or the person delegated by the administrator, we would share that internally with NASA, and the path forward for sharing that externally is still TBD.
All right, thank you so much, Dr. Shah. There's going to be some really big shoes to fill to keep that work going. We're going to turn now to what I would consider arguably the signature metric for longitudinal surveillance and health outcomes, and that is the ionizing radiation that we're exposed to. And we do not have a radiation panel this year, and I think that it is appropriate now to discuss a new change in our outlook on radiation within the rubric, if you will, of lifetime surveillance. So we have made a quantum change in our expectation for radiation limits, exposure limits in flight. And I'd like to touch on two aspects of that today with two speakers. Now, we're going to talk about a proposed standard which is being discussed. The final decision has not been made, which I think it makes it somewhat timely to share with this group. We will have Dr. Elgart talk a bit about the new radiation standard, what it is, what it means, why we did it, followed by Dr. Antonsen to talk about that long-term health outcome. How do we monitor? How do we measure? How do we attribute? How do we manage this risk, if you will? So first with Dr. Elgart. Dr. Elgart has degrees in microbiology and a PhD in biomedical physics from the University of California, LA. And she worked with DNA damage response following low-dose radiological exams in patient samples. So I think she's very acutely aware of the health outcomes of this exposure. She has served as subject matter expert in space radiation health risks for NASA for quite a while with the SRAG, the Space Radiation Analysis Group that I think some of you are aware of. And more recently, last year, we snagged her to be our element scientist in the space radiation element of the Human Research Program. So she's working very hard to help us work out the exposures, the physicality of this risk for expedition forward missions. So with that, Dr. Elgart, I'll give the floor to you.
All right, thank you so much. And can I have a quick comm check?
Got you loud and clear.
Great, thank you. So good morning, good evening, good afternoon, wherever the heck y'all are. I am delighted to be here today and would like to extend my gratitude to the organizers for inviting me, of course, to share this time with you. So Dr. Barratt specifically asked me to touch on what's happening with this new proposed radiation standard. And the long and the short of it is that the Office of the Chief Medical Officer initiated a review of the current standard and how radiation risk is communicated back in the beginning of 2020, which honestly feels like the beginning of time at this point. And so you see the current standard, because this is still in the proposed standard is still in it's an agency-wide review, so it's not fully official yet. So the current standard, as it's written right now, is only applicable to missions in low Earth orbit. So it's essential that the agency defines a standard that considers both LEO and exploratory missions as we move on towards Artemis and out towards Mars. And so the current standard limits astronaut occupational radiation exposures to a level that increases their excess, important term there, excess lifetime risk of fatal cancer to 3% at the 95% confidence interval. All right, so you notice it's a risk-based standard, and it's also communicated using risk. The model that's used to calculate what an astronaut's risk is based on their unique exposure profile. Maybe you went to the moon way back in the day and you did a couple of ISS. That's your unique exposure profile. And also takes into account age at exposure and sex, whether you're male or female. This type of limit results in every astronaut having what is essentially their own personal exposure limit. So after discussing terrestrial radiation protection strategy practices and clinical insights into cancer risk with a small panel of experts following the initiation of this review, the OCHMO standard manager proposed a new radiation standard, which is still based around a 3% risk, but it's communicated as a single dose-based limit, regardless of age or sex. So the proposed maximum allowable effective dose is 600 millisieverts, and that was selected by considering what we consider the most susceptible case, that of a 35-year-old female. So the case that we considered took into account age at exposure and sex, but we're communicating it as a single dose base limit of 600 millisieverts. And so to put this in perspective, our international partners, CSA, ESA, and Roscosmos all have career dose limits of 1,000 millisieverts, so about 400 millisieverts over what we are proposing now. And JAXA uses a risk-based limit that is centered at 3% and is still age and sex dependent. So it ranges from about 500 to 1,000 millisievert. They cap theirs at 1,000 millisievert as well. So the new proposed standard is well within the ballpark of what our international partners are doing. And so from the perspective of lifetime surveillance, to bring it into what we're talking about today, as well as the human research that we conduct, which is, of course, my primary focus as the element scientist for space radiation element, I believe, and this is my personal own opinion, I claim no responsibility for anyone else's, I believe the proposed standard provides the opportunity to investigate and communicate aspects of risk like individual susceptibility more deeply and offers crew more autonomy in their decision making when deciding their career paths. So more nuanced aspects of risk characterization like family history, genetic susceptibility, which is normally something we cannot talk about when we talk about standards for legal reasons, and lifestyle factors can now be interrogated and included in more personalized risk estimates that won't impact flight eligibility. And so now these will provide information to the crew, their families, and their health care providers, including their flight surgeons, as well as the agency, to make more informed decisions about their future, which I think is really important. We can really start to personalize longitudinal surveillance for crew based on their individual needs, rather than providing a one-size-fits-all solution. And therefore, one of our top priority research areas is identifying and developing early disease detection, not only for cancer, but also for cardiovascular disease and any changes to the central nervous system that can impact behavioral health. And now, as Ronak pointed out, with the TREAT Act, we can actually support our crew more robustly, even into retirement, when the impacts of space radiation are anticipated to present themselves. So I hope I've given you a little bit of insight into what the new proposed standard is and why, from the research perspective, I think it gives us a lot more flexibility of doing the right thing by our crew. So I'll pass it back over to you, Mike.
Okay, I appreciate that, Dr. Elgart. It's worth saying that the crew office has been very involved in this process from the outset. Dr. Antonsen actually involved us extremely early as we were laying the groundwork for this. And to just emphasize that the new standard still puts us below most of our international partners as far as their permissible exposure limits. Having said that, I believe our radiation community agrees that nothing absolves us of continuing to study this as aggressively as possible, which I think you're describing there very well. So I'm going to go right to Dr. Antonsen then, and we may have a couple of questions for both of you before we go on. Now, Dr. Antonsen brings a lot of skills to the table. We're very lucky to have him in our program. He has master's and PhD degrees in aerospace engineering from the University of Illinois. He did his medical training at the University of Illinois Urbana, and he did his residency in emergency medicine at Harvard. So he's still a practicing emergency medicine physician. He serves as associate professor of emergency medicine and space medicine at the Baylor College of Medicine. He's worn several hats at NASA, along with doing all of these things. That's included being the element scientist for the exploration medical care discipline that we have, and was our former chief of the Human System Risk Board. He thinks extremely analytically. I have found that pretty much nothing escapes this guy's look when he's looking at a problem as holistically as possible. And with that, I'd like Erik to talk a little bit more about this long-term risk management stance that we have towards radiation.
Thank you. Can I get a quick comm check as well?
Loud and clear, my friend.
All right. So I appreciate the opportunity to speak here. One of the big drivers for this change in the standard for radiation was the recognition that over time, we've struggled to try to align our expectations both clinically and analytically for the radiation risk as it has stood with all of the other risks that we've managed among the agency for astronauts. We carry about 30 of them, and radiation carcinogenesis is one of those risks. It's a unique one because the bulk of the things that it covers are long-term health, things that happen after the flight career for astronauts, whereas most of the other risks are really centered around things that are in mission. What's happening to the crew? Can they do the job that they need to do in a mission, whether it's in low Earth orbit or whether you're looking out towards what we're doing at Mars in the future? So over time, there had evolved a different way of assessing that risk that had resulted in some divergence. And part of the challenge for that is that when we think about what is it that we need to invest in, where do we need to put research dollars, where do we need to make sure that we're allocating all of our investments and capabilities in reducing risk for astronauts, part of the challenge in prioritizing all of that really depends on making sure that you're doing an apples to apples comparison between the competing risks that astronauts face in spaceflight. And so while there are long-term health risks from cancer and carcinogenesis, there are, as Robin mentioned, some other ones that radiation touches on, right? Cardiovascular challenges that we have, central nervous system, and some other that radiation doesn't play as much of a role in, maybe. Things like what happens in terms of your bone health and your muscle performance after your career. So there's a whole variety of those things that need to be rolled up together and need to be communicated in a common way, not just to the astronauts, but to the decision makers within programs and to the decision makers at the Office of the Chief Health and Medical Officer, all those folks that are sitting around a table trying to say, what are the biggest problems that we face and where should we be putting our effort into this? Now, along with all of those other risks, many of which focus on in-flight things, they all have aspects, almost all of them, of long-term health consequences that we consider. This is a unique part of NASA. The program managers that are putting vehicles up there for astronauts to work within, oftentimes their responsibility ends when somebody splashdowns. It ends at the end of a specific mission. But the Chief Health and Medical Officer, the Health and Medical Technical Authority, and all these other groups that look at the health of astronauts, they have an ongoing responsibility long after those astronauts have finished doing their job. And that's part of why the TREAT Act, as Dr. Shah was talking about, and the radiation standards are something that we constantly look at. So what are the implications for that in terms of lifetime surveillance? Some of the recent investments that NASA's made in terms of trying to upgrade all of the ways in which it is able to capture data for our astronauts. Remember, Dr. Shah mentioned the 47 plus 20. We have an evolving evidence base that's expanding over time, not just from the perspective of looking for cancers, but also, are we seeing fractures in our astronauts earlier than we would expect to see for a common cohort? Other health implications, right? All those things that we need to follow, we've been trying to work to update. How do we do that process? Within the lifetime surveillance of astronaut health and within the data management capabilities that NASA has worked, there's been funding going towards a program called Impala, which is something that allows us to start to move some of the management of that data out of very manual processes that take a long time to interrogate that data into more data analytics processes and capabilities that allow us to get faster decisions and faster input back to those decision makers at NASA. And the goal for all of that is to tie some of what we're learning from lifetime surveillance of astronaut health back into the process of risk management that looks at what should we be doing about that today. The biggest challenge from the cancer perspective is that the lifetimes, the length of time that we expect to see the development of cancer is such that that's probably one of the most lagging ones that we're going to be able to feed back information for. But we actually do see some of that information come back in other places, like in bone health, that help us to decide, hey, how big of a problem is this? And should we be trying to do more with it? And it's that right sizing of that risk metric across all of these different things that we have to struggle with, not necessarily just prioritizing one thing. That is the job of the agency and the Health and Medical Technical Authority as they look at risk across all of these things. One of the things that came up when the National Academies reviewed this proposed standard and the reasons for why we're looking at changing it was that the 3% level has been something that's been in place since about 1989 for NASA, and that there are good reasons to go back and reassess whether that's even the right level to set these at. And the way to do that is to make sure that we're leveraging the best information that we have from lifetime surveillance across all of these things to make sure that we're comparing that to other hazardous industries, that we're comparing it to the other risks that we carry. If we have medical problems that occur in spaceflight that cause long duration problems down the road, how do we weigh those against the radiation cancer particular risk? And that's a unique set of problems that we struggle to deal with because we have imperfect data collection systems. We've collected this data over all sorts of different exposures with different people in different vehicles with different sensors, right? So we have a very challenging problem when it comes to risk management overall to right size radiation along with all of the other risks that we face and make sure that we're doing our best to improve those systems and ask these questions periodically over time. Where's the right place to put our yardstick? Where's the right place to plant our flag for protecting our crews? And how do we make sure that we have invested appropriately in those lifetime surveillance capabilities that can feed back into our systems today? So I'll stop there, and I hope that helps set some of the context for this.
No, I think that's perfect. And I think your description of the approach to the problem, which is right-sizing the risk metrics into the context of the program holistically is really what we care about, both as program management and both as crew members, as consumers of radiation, as I call it. So I appreciate that. I'm going to march down the line with our speakers so that we can try to be fat for question time if we can. We'll flip gears a little bit, and we're going to go to Dr. Rahul Suresh. Dr. Suresh, who I had the pleasure of spending about a month in quarantine with recently with the Crew 3 launch that just arrived at the space station on the Dragon craft Endurance, comes to us from the UTMB program. He has a master's degree in clinical and translational research and his medical doctorate from Mayo. He trained in internal and aerospace medicine at UTMB, where he also obtained his master's in public health. He has joined us, and we're very fortunate. He's an ISS and Hawthorne console certified NASA flight surgeon. Some of you may not quite get what Hawthorne means. That means SpaceX. That's mission control SpaceX, if you will. So he has cut his chops there and has learned basically a new spacecraft and a new infrastructure to work in, along with a few of our other flight surgeons. He's been working as a certified flight surgeon at NASA for the past couple of years, and he is currently the prime crew surgeon for the Crew 3 mission. This is Expedition 66, currently on board the space station. Now, what I've asked Dr. Suresh to touch on is the private astronaut mission program, which is really starting just now. We anticipate a crew, the inaugural crew with the Axiom 1 mission early next year. This constitutes many things. It's a big shift for us to have non-NASA people coming to the International Space Station, but it also creates a lot of that information that helps us to kind of round out our knowledge of the human response to spaceflight. I'd asked Dr. Suresh to help paint a picture of what the PAM program is like, what it means, and what we can expect in the future. So over to you, Rahul.
All right, thanks, Mike. Quick comm check. Can you hear me?
Got you loud and clear.
Great. Well, thank you for having me today. To Mike, Mr. Abbey, and the Baker Institute. I'm really excited to share all the things that have happened in the private astronaut mission world over the last year or so that I've been involved. And I can say that things have taken shape very quickly, and we often find ourselves defining the integration process with these providers while simultaneously implementing them. So it's led us to a wealth of knowledge and lessons learned across the spectrum, including human research. So I'm excited to share that with you guys today. Just so that folks have a shared understanding, the private astronaut missions are a unique paradigm shift in how NASA supports and frankly the ISS supports flying private astronauts. And specifically in this paradigm, the PAM provider is fully responsible for both the safety and the success of the mission and in mission execution. And NASA's primary responsibility is in levying requirements that ensure ISS mission success and ISS crew safety during integrated operations. So from a PAM provider perspective, they're responsible for all the things that typically NASA or one of the international partners would be in executing a mission to the ISS. This would include things like provision of necessary supplies, life support and medical care, acquiring the appropriate transportation services, selecting, training, and medical qualification of their private astronauts, upmass, downmass, stowage, and real-time mission support. So as Mike mentioned, the upcoming mission is slated for no earlier than February of 2022, and it's intended to be a 10-day duration, 8-day docked with 4 private astronauts and 2 to 3 backups. The launch provider will be SpaceX, and the overall mission objectives are education and outreach with an expectation that the crew members will perform some additional marketing and science activities. So I'll start just briefly outlining the medical risk assessment and disposition process, because again, the role that NASA plays here is different than what it is for our astronauts. So the PAM provider is responsible for the selection and medical certification and pre, in, and post-flight medical care of their astronauts. We have, NASA has published through the Office of the Chief Medical Officer, the medical policy outlining how NASA will levy medical requirements on these providers and on these crew. And the process is that the PAM provider is responsible for the medical certification or medical certification packages of these crew, and they will present these to NASA for review of the risk of these crews' medical status to our crew and our mission, and for risk approval by NASA and by the IP partners. And it's important to note that, again, the paradigm shift is that NASA is not certifying these crew, and neither are the international partners. So from a process perspective, we consider there to be two essentially categories of private astronauts. There are private astronaut crew and private astronaut spaceflight participants. Private astronaut crew are those who are considered to be performing hazardous tasks or tasks that include use of high criticality hardware such as EVA, robotics, or piloting the vehicle. And then all others are considered spaceflight participants. And this is an important distinction because the medical requirements applied to each of these groups is different. So for those who are considered private astronaut crew, they will be held to what we call SSP 50667 or Med Volume A, which is the same standards that we use for selection and retention of our NASA astronauts and of our international partner astronauts for flight on ISS. Alternatively, for the spaceflight participants, their medical requirements are dependent on how on the length or duration of their flight. So for those who are flying on a short duration mission, which is considered less than or equal to 30 days, they'll be held to a portion of Med Volume A called Appendix F, which is an abbreviated set of medical requirements compared to, again, what we use for our NASA astronauts. And then if they're flying for a long duration mission, which again, there are no slated missions of that duration at this point, but we anticipate such missions. For those missions, private astronauts will be held to the full Med Volume A, such as the private astronaut crew. Interestingly, NASA is not levying requirements for medical surveillance in flight, or what would be considered our Med Volume B, Medical Evaluation Document Volume B. And so it is up to the provider whether or not they choose to perform these evaluations in flight. The evaluations will go through a series of boards, again, starting with the Aeromedical Board at NASA, then proceeding to the Chief Health and Medical Officer, and then finally to the Multilateral Space Medicine Board, which is comprised of members from the international partners. Once that process is complete, they'll go to the Multilateral Crew Operations Panel, or MCOP, for final acceptance. In addition to medical review, there's related evaluation by our Flight Operations Directorate to ensure that these crew are suited for this extreme environment, which can be highly stressful and isolated. And so there is a separate extreme environment experience requirement and evaluation process, as well as a behavioral health and suitability evaluation that's separate from the psychiatric evaluation that they undergo as part of the medical review. I'll briefly touch on the medical operation. So again, because the provider is responsible for all aspects of mission support, they will be responsible for executing a health stabilization plan, which will be reviewed by NASA, but will be executed by the provider. They are responsible for providing ground medical support, including crew surgeons and behavioral health specialists. And they will conduct their own private medical conferences and private psychological conferences. They'll also fly their own medical supplies that are defined in part by NASA to cover common medical conditions that we expect and know occur based on our decades of spaceflight experience. But beyond that, what they fly will be up to them and what they see as a priority. In addition, NASA recognizes that the PAM provider does not necessarily have the same capability from a medical standpoint that the ISS does. So we expect that in a contingency where the medical capability required to treat their crew members exceeded their capability, then we anticipate making resources available to the PAM provider with permission from our onboard CMO specialist and flight surgeon. From a research standpoint, we've learned a lot, as I mentioned, over the last year as we've integrated this first mission with respect to payload development, sponsorship, and integration. That process, just briefly, starts with the crew member. So what do the crew want to participate in? who do they want to collaborate with as far as institutions and investigators. And some of it obviously is driven by the provider themselves and what they wish to promote. Institutions and investigators, as I mentioned, partner with the crew member and with the PAM provider to develop and implement their payloads. Ultimately, the PAM provider is responsible for then pulling together this entire research complement that includes research for each of these crew members and from many different sources in conjunction with the ISS National Lab. Finally, NASA will then accept that integrated complement to then perform final integration activities for flight. We've recognized some important considerations in this integration process that I think will inform the types of activities that are feasible and the number of activities that are feasible for future missions. The total number of payloads is an obvious one. NASA has a historical sort of baseline of how many payloads we attempt to execute during a mission, and the provider may have either more or less payloads than that, and as the payloads increase, the complexity increases. The number of crew members participating in any specific investigation obviously increases the choreography. The total number and volume of biological samples collected has important implications and must be pre-coordinated. There are obviously pre-flight and in-flight hardware and supplies that are needed to support investigations. Some of these are owned by HRP, some of these are owned by medical operations, and then of course the provider may fly some of their own supplies as well. And so depending on what agreements can be reached will determine what payloads or what investigations can be executed during these missions. Up mass and down mass is a consideration, including condition storage, as well as whether pre-positioning will be required. These crewed vehicles have very limited cargo capability, and so sometimes required supplies need to be pre-positioned. And then we've had to work through some legalities of involving international investigators for taxpayer-funded resource, which is the ISS National Lab. From a data sharing perspective, we've just started to scratch the surface. We've spent most of the past year establishing just the process of integration, and so the resources available to really dig deep and begin the process of identifying where data sharing can happen has been limited. And so we do look forward to expanding on that in future missions. From a NASA-sponsored payload perspective, NASA has elected to include HRP standard measures, cross-cutting investigation as an option for private astronaut crew to participate in. For those who are not familiar with it, it is a standardized protocol to collect certain parameters, including physiological, biochemical, psychosocial, and cognitive data. And these parameters have been proven to be paramount in understanding changes in functions of human body in space, and can be used longitudinally to answer a multitude of operational, occupational, and research-based questions, and of course, feed into our risk mitigation understanding. So inclusion of PAs in this investigation has some benefits. It can increase our sample size of investigation, and it includes individuals that potentially have a broader spectrum of underlying health conditions that can inform future flights for both those types of individuals, but also our own astronauts. Of note, NASA was unable to support integration of standard measures for Axiom 1 due to, again, resource constraints, but we look forward to being able to do that in the future. From a PAM provider standpoint, NASA has primarily served in the upcoming mission as a facilitator and not in data sharing, active data sharing. We've made available, for example, a number of resources such as the OCT2 device, the onboard cycloergometer or CVIS, and a number of other resources that are needed to execute the payloads that the crew members wanted to support. And so this has been a great opportunity to understand what NASA can support and what NASA cannot support. Interestingly, NASA crew are not participating in any of the Axiom payloads. So again, there's not really an opportunity for data sharing there either. But in the future, this may change, and it'll be interesting to understand where it makes sense for collaboration and with future providers. I will just close by saying that the upcoming Axiom 1 mission obviously is occurring in February, but we do have the impending announcement for PAM2 and possibly PAM3. And so we look forward to learning who those providers are going to be and to working with them. Thank you very much for your time.
All right. Thanks, Dr. Suresh. I think one of the important points here is that these guys, they're not just arriving as private astronauts, they're arriving with a whole new medical infrastructure of support and basically end-to-end care. I will say from a crew standpoint, I've flown with 2 spaceflight participants before. We've done that 7 times to the Mir station until just recently, and now they're going to be coming more than one at a time. That's going to be a whole new dynamic for the crew on board that has a busy schedule. So both from the Russian side and the NASA PAM side, we look forward to a lot of changes. But I think these are ideas that whose time has come. I'm going to switch next to Dr. Dorit Donoviel. For those that know her, her position description is pretty much synonymous with her name. There's only one Dorit Donoviel, but I will mention that she has a background in biochemistry from UCSD and a PhD in biochemistry from the great University of Washington. She has done many years of further research postdoc at Mount Sinai Research Institute and many years in biotechnology industry, which includes drug discovery, project management. She has directed multiple diverse concurrent projects from inception to pharmacology, familiar with drug approval process, all sorts of practical things that are very relevant to what we're doing. And currently, just skip to the end there, she serves as the executive director of Trish, the Translational Research Institute of Space Health, and also as associate professor of space medicine, Baylor College of Medicine. And I've asked her to talk a little bit about involvement with capture and standardization of biomedical information from the commercial world at large, not just limited to the NASA PAM mission. So over to you, Dorit.
Thanks a lot, Mike. This has been tremendous. So Rahul, I was taking feverish notes on everything because I don't think anybody's actually laid out for us exactly what was involved with working with this first private astronaut mission in integration with ISS. So this is a first. So I appreciate all the details. So Trish is a agile partner to the agency, to NASA. We work very closely with the Human Research Program, and our job basically is to be opportunistic, to look around corners and find things that the agency itself may not be in a position to capitalize on in order to reduce the risks to astronaut health in space. So we quickly realized the opportunity was now to collect as much as we can data samples from all of these private astronauts that are going into space. And so I understand what a logistical complexity task it is to integrate with the ISS program for the Axiom mission. But we were ready when SpaceX was going up with 4 orbital flyers, their very first free-flying commercial mission with Inspiration 4, in order to collect some samples from them and to collect some pre and post data. Sensory motor was certainly of importance for us, as well as in-flight testing of medical devices to see whether we can actually learn something, for example, on the risk of blood clotting in the internal jugular vein. We wanted to make sure, and we were there. So what we're trying to do is capture all of the private astronaut data and samples at the very minimum, pre and post flight, at the very minimum, get some sensory motor data, some blood collection, and whatever we can that is not easily integratable with, for example, ISS. So even for the Axiom 1 mission that's coming up, HRP really was intending to do standard measures, but as you mentioned, there was a resource constraint. And so we were able to come in and at least collect some pre and post-flight data and samples from the Axiom 1 crew, so we're working closely with them. What's critical about this is that standardization of data collection is really important so that when we, in the future, have 20 years worth of not only biological samples, but also data from all of these private passengers, we actually are able to compare apples to apples. So while there may be differences in the types of missions, the mission duration, the providers, whether it be an orbital flight with SpaceX, a space adventure flight with the Russians, or a Axiom flight flying to ISS, or a Blue Origin flight of the future, or Sierra Space flying on their Dream Chaser, we're going to be able to collect all of that data in a standardized, unified manner. What we've established actually with the Inspiration 4 flight and are now about to add to that data set, working with Space Adventures for their upcoming flight with the Japanese nationals. So we're thrilled to say that we have a consent from a Japanese participant that's flying on December 8th, and we've already collected baseline data as the mission is now coming up, is to take all of that data and put it into a database, which we call the Expand database. And it's really quite a remarkable, capable product. We actually looked very carefully at about 25 different market available capabilities. So these are software platforms that serve the pharmaceutical industry in capturing clinical trial data. So they're able to take in both clinical and research data in a longitudinal manner. And we've put in place the very best that we can find out there that is very agile in the sense that it could take in different types of data sets. So ranging all the way from environmental sensors from the vehicle in terms of CO2 levels, altitude, temperature, radiation levels, all of those things, and correlate that in a time-stamped manner with the physiological data that we collect from the sensors that we put on the humans themselves, or the data that we capture through some of the devices that we send up, and correlate all that with samples. And so being able to capture DICOM images from ultrasound scans, as well as even surveys that the astronauts themselves will be taking. So this database provider will be able to integrate all of this, and in such a manner that it will be easily queryable by the research community. So once you've kind of put in enough data sets, roughly 6 to 8 data sets, you can start to provide a little bit of a subject identity protection. So all of our data sets will come in and will be de-identified, but as you know, there is such a small subset of individuals and data sets that one really does have to be careful in terms of like collecting enough so that we can protect the privacy of the individuals. What the other thing is that what's really important to do here is to make sure that you put in place data sharing agreements from the get-go. So one does not have to worry about going back and, you know, when we're querying, for example, a data set that was collected from a researcher at University of Pennsylvania, that data sharing agreement is already in place, and that does not have to be negotiated. And so having all of those universities and companies work together from the very beginning to agree to one common data sharing agreement and intellectual property understanding, as well as the providers, for example, SpaceX and Axiom and Sierra Space and others, everybody has an understanding from the very beginning about how we would share data, who would own intellectual property if there was anything commercial that comes out of it, and what is going to be considered just, you know, academic-based research. The other thing that's really important is we've recognized that each provider themselves is very protective of their own data sets. So for example, Blue Origin may have a data set that they may want to contribute to this database, and they may want to keep that separate, certain things that are only available to Blue Origin to access versus a SpaceX data set. So we are able to parse out these data sets separately as well for each of the providers. So it allows all of these companies in the marketplace, they may be competitors, but in terms of being able to work together as a community to collect a data set that will actually be useful and in improving our understanding of the risks to some of these private passengers that go up to space, and also inform on the astronaut risks as well, as we think about perhaps some of these medical conditions that some of these individuals may be flying with today may develop in a future astronaut, a government astronaut. So contributing to the whole knowledge base together. Finally, what's really critical is we have been able to work out one institutional review board protocol and consent form. So rather than having multiple consent forms and multiple IRB protocols from the various investigators, we have put it into one, and all the institutions have agreements with this one IRB protocol. And the consent form that's done only once with the participant is a wide-reaching consent form that allows us to actually continue to do work as long as it's about informing human spaceflight and risks to humans in space in the future. So if a new assay or a new capability is identified in the future, we do not have to go back and reconsent that individual. We have a far-reaching capability of looking at that individual's data, again, with all the privacy protections that we could possibly put in place. And so we're really excited about that capability. And what we plan to do with all the sample collections, the pre and post flight and in sample data collection, is not just to store the samples. We will keep some of the samples, but actually do a very wide standard set of omics analyses. And so the proteomics, the metabolomics, the genomics, the every omics that you can think of. And we're very lucky because Baylor College of Medicine itself is a home of the Human Genome Center, and there's a lot of expertise here. And we're also working with Weill Cornell, which also has a lot of expertise to kind of do all the baseline omics. And that way we could store the data in a raw format. And so individuals, researchers can come in and query the data, and it's already been kind of partially analyzed. And so we will also retain some samples in the future should a new type of assay will be thought of that we hadn't considered today. And then the last point I'm going to make is that at least half of the private participants are internationals. It becomes a lot more complicated when you go outside the US and you're trying to make sure that the subject protection laws and privacy laws of other countries throughout the world are also considered as we're engaging additional research participants. For the Japanese participant, for example, Russian participants, Europeans, et cetera, et cetera. And so our ability to work with a one IRB entity that allows us to look at all of these different countries' rules and regs, as well as the database provider that has experience working in the international agreement arena, also ensures that we are able to handle international data sets and samples. And so with that, I really thank Mike and for inviting me to speak about this, and we look forward to absorbing any data that is not currently able to go into the NASA database. Thank you. Thank you.
All right, thanks, Dr. Donoviel. That was really, really interesting. I encourage everyone to visit the Trish website and get a feel for what the organization does. She touched on a lot of things about data and how it has to be protected from the standpoint of proprietary information, intellectual publication rights, and of course, medical privacy. But in general, we don't want anyone to have to rediscover something or to reinvent a wheel that someone else knew about. We really need to share this data, do it carefully, do it methodically. So I appreciate these efforts. We have about 15 minutes left in our session, and I want to give Dr. Wagner and Dr. Van Baalen a good time, but I'd like to ask my panel recipients, if you check the Q&A section, if there's a question that's relevant to you, please go ahead and answer it, and we can do that real time and try to stick to our schedule and make sure that the next panel is ready to go. So with that, I would like to introduce Dr. Erika Wagner. She is one of the products of the very productive manned vehicle lab at MIT. She has a multidisciplinary background in aerospace and biomedical engineering with significant exposure to both spacecraft development and clinical medicine. Very unique combination. She has research expertise in vestibular physiology, bone biomechanics, organizational innovation, and actually prize theory, and in particular how the X prizes have served to stimulate the spaceflight activity. She currently is serving as the payload director, the payload sales director for Blue Origin, where she facilitates research, education, and other aspects of utilization for both the New Shepard and the next generation spacecraft that are coming. So these are all commercial space station initiatives, commercial spaceflight initiatives, and of course, the newly announced orbital reef station, which is coming, a very exciting proposal. Her interdisciplinary background includes degrees, again, in biomedical and aerospace engineering, focus on human and mammalian adaptation to novel gravitational environments. And I've asked her to come and talk a little bit about biomedical research opportunities of suborbital flight, this program which is just starting and expected to be flourishing as a new channel of spaceflight data. So Dr. Wagner, over to you.
Thank you so much, Mike. It's so nice to be here. I think one of the things that's really striking to me as we listen through these talks is that commercial spaceflight arena really has that trifecta. We have government career astronauts and occupational health issues. We have commercial spaceflight participants and what they may be looking for as a buyer of services. And of course, we have on some platforms commercial astronauts with their own industrial occupational health topics to be covering. So it really does touch on this in some pretty unique ways. We are flying our New Shepard rocket, coming up on our 19th mission, our third human flight, and going into a more and more regular cadence of flying astronauts from a wide variety of backgrounds. And as we've done that, we've been finding that there's a surprising, maybe to some of our team, interest in those spaceflight participants in taking part in what's going on in the research world. We're also working pretty actively with NASA's Flight Opportunities Program, which funds commercial and academic researchers, and the new Suborbital Crew Program, which lives underneath commercial crew, which is designed when vehicle qualification efforts are done to make way for government civil servant astronauts to be flying with their own research. And that means any civil servant at any NASA center or NIH, NSF, Space Force, et cetera. So really interesting set of programs that are opening these doors to more and more people flying, either hands-on with their own research or as participants in research. And when I think about where this plays a role, it really sort of falls into three categories. There are ways in which we are extending the laboratory to space for highly skilled researchers. As much as I love our friends in the astronaut office, they're often getting just a few hours of training on science. Some experiments really do benefit from someone who spent 20 years in a lab with their hands right deep in the experimental hardware. The second opportunity here is extending the data sets from small populations to very large ones. So we look at the forecasts of Blue Origin, of Virgin Galactic, and of others, and we're very quickly going to double the total number of astronauts that have ever flown in space. At least that's the industry's plan. So how do we look at those large N biomedical responses to spaceflight, and how do we use that? And then the third is for training astronauts, training crews, training teams in operationally relevant environments for full end-to-end mission operations. So I think we're going to be learning a lot in our collaborations with Trish on how do we help get the next cadre of researchers, ground crews, flight surgeons, et cetera, to have those experiences on a regular basis of working with crews. So when I look at the kinds of experiments that have been coming our way, they really sort of delve into two unique buckets. One is the unique subjects and interventions that we can fly. That's not traditionally possible on ISS, or certainly very difficult. And the other is things like protocol and hardware maturation. So let me just spend a little bit of time on these unique subjects. So our qualifications at Blue for flying on the New Shepard suborbital vehicle are very much functional. If you can climb our 6 flights of stairs in 90 seconds and you can get in and out of the capsule, you can put on your own flight suit. Today, that's pretty much the qualifications for getting on board. These are 11-minute missions from end to end. So the risk profile is somewhat different than when we look at long duration orbital exposures. So within that functional set of requirements, and I'm happy to share a set for those who are interested, we are always trying to look at ways that we can open that more broadly. How do we fly individuals that have never been able to fly in space because of underlying medical conditions or medical devices or other things that have traditionally been exclusionary criteria? And how do we do that safely? We've looked then at how we use that unique population to interrogate systems that are really hard to interrogate in our perfectly healthy 47-year-old astronauts on ISS. And there's some great history there in what's been done on the parabolic flight aircraft campaigns, where we've been able to actively engage patient populations, folks with unique physiology. You can, some of the studies that have been done in sands with indwelling reservoirs, so you can do direct measurements of intracranial pressure, or things that are short duration in physiological time constants, so pulmonary deposition in the lungs for drug delivery or dust mitigation studies, things like acute imaging of the venous stasis situation as we go through various environments from launch through microgravity, through reentry. And on a platform like this, you could imagine using catheterization or contrast in ways that would be much harder to do on a station like ISS. So we look at those opportunities for challenging the body in unique ways, for using bodies that are already uniquely challenged in their own ways, and for doing large end population studies that give us a lot more insights. So I think that I'll point out that in addition to the very active work in suborbital, as Mike mentioned, we've got the orbital reef, our commercial space station coming down the platform design pathway. The intention is for our team of Blue Origin and Sierra Space and a wide range of other contributors to have a platform in LEO before the ISS is ready to retire. So we are very actively working on that, thinking a lot about crew training and crew qualifications and our own medical programs that are going to provide an end-to-end service that supports, again, that trifecta of industrial users, government astronauts, and commercial participants. So I very much look forward to talking. Please don't hesitate to reach out. You can reach me at payloads@blueorigin.com. Thanks.
All right, thanks, Dr. Wagner. Just to be sure, if people want to know more, short of contacting you, which I encourage people to do if you are willing, the Blue Origin website, is there a place that they could go to get a little bit more of the life sciences bent?
So blueorigin.com/payloads has a bit about all of our applications there.
Okay, so big opportunities. There's diversity, but hopefully unity in the human spaceflight community to bring all this data together, and that's kind of what I'm hearing here, which is great. All right, last but not least, Dr. Mary Van Baalen, and I'm going to give her the impossible task, but we do that all the time with Mary to try to sum things up here in about 5 minutes. There's a reason she's the last one here. I'm gonna be incredibly and unfairly short, but she serves as our Assistant Director for Human System Risk Management. She has leadership oversight over the Lifetime Surveillance Program. NASA's epidemiology group was huge. The operational implications of the integrated medical model and the life sciences data archive. This is basically the backbone of NASA's data evidence base that we use to answer all of our questions and leverage for risk assessments for mission, career, lifetime risks to the astronaut population. All of this is meant to be public domain and shared. I can't tell you how many times the answer to the question is ask Mary to go find out with her team. So with that, I'm going to give it over to Mary, and we're going to do our best to get the next panel online in 11:45. But short of publishing her cell number, hopefully Mary can tell you where to find some of the resources that support what she's about to say. So over to you, Mary. Did I scare her? You're mute, Mary.
Sorry. And you guys can hear me? Okay.
Gotcha, loud and clear.
All right. I did ask Mike to make me look good when he introduced me, and it does help me as I go through this. I did have some prepared marks, but what I was going to say is I do think that in this multiple roles that he described that I currently have, it gives me a unique position to kind of look across NASA's data sources to try to help answer questions and try to help work in enabling the human system risk management. And so he did describe two of my roles. And the one that most of this community is familiar with is my management role of both the LSDH and LSDA teams. And I'm going to use this opportunity to shamelessly market it as a data source that we have used from a longitudinal fashion for the last 60 years. For the community at large, we'll remind you that the LSAH archive is all of the medical data that has been collected since the late 50s until present. And so it's structured in a longitudinal fashion of the astronauts over their careers, from selection and into retirement, as Ronak described. The LSDA is since 1958. It's an archive of all of the research data that has been collected by NASA. All is probably a strong word, but the vast majority of the life sciences research data that has been collected by NASA as well. These two archives together provide a unique resource for combining to be able to evaluate the longitudinal nature of the data. They also have a really unique opportunity to be combined with the data sources that my co-panelists have talked about here. So this is a future that I see very exciting. I hope to be able to leverage what we've been doing with NASA's data with these other types of efforts to help further the answers within spaceflight. My more recent role is acting chair of the Human System Risk Board. And for those of you outside of NASA, NASA does every decision-making process kind of with a board. And so the Human System Risk Board brings together the large life sciences community at NASA to talk about the 30 different human system risks. Each risk is composed of kind of a risk custodian team, a 3-member team of an epidemiologist, a physician, or operations individual, and a researcher. We'll bring all that evidence together out of the archives or prospective research to try to help educate and understand the risk. Erik talked wonderfully about what we're trying to do as we inform the risk to work towards solutions to buy down that risk. One of the things I will point out is, again, there are 30 system risks. Human physiology does not live in an isolated risk. It's a very integrated approach and should be an integrated approach across the human physiology. So when we look at the risk, we got to start looking at integration of those risks. And we need data areas to help with that. I'm kind of hoping I'm making a nod here towards the complexity of human system risk management. I'm also hoping that what I'm doing is helping the community to understand why we need these various approaches to data collection as described in this panel. Bringing all of this stuff together to understand the human system risks for spaceflight is challenging, especially when you consider the fact that the human international space community has been collecting data for over 60 years. Data formats have evolved, medicine has evolved, approaches to research have evolved. I mean, this longitudinal collection of data and its reuse requires investments in data harmonization efforts and IT systems that can help enable this use. Erik talked about the medical data archive, the investment in Impala, but I also should market to this community that the research data archive is undergoing an investment at this point. We call it the Insight tool, or the next generation LSDA tool. And what we're hoping to have is 2 integrated, improved IT systems that will allow us to harmonize that data in a more automated fashion, less manual as described. These harmonization efforts in the IT systems will also enable the use of analytic tools. And that, I think, is going to be important. There are current analytic tools that are hard to apply against data sources that have been collected 50, 60 years ago. I want to ping a little bit on what Rahul said. The trained epidemiologist me has to point out that looking at these data requires creative scientific thinking combined with these advanced analytics capabilities. The number of individuals flown in space is really small, and it has been a largely homogeneous population. That actually has served NASA and the current international space community well, because with a homogeneous population that's largely healthy and largely similar demographically, it's easy to be more generalizable. Adding new spaceflight participants should also make that a little bit more generalizable to the across the general population. Excuse me, same words over and over again. And anyway, in conclusion, I actually would like to quote Carly Fiorino, with a former CEO of Hewlett Packard, with the statement of, the goal is to turn data into information and information into insight. And that is actually what we're trying to do. And I'm very encouraged by the changing landscape of spaceflight here that we've described, and the ability to get new insights. So thank you, Mike. Back to you.
All right. Thanks so much, Dr. Van Baalen. A lot of this you can see online at NASA's sites. I really encourage people to use the Life Sciences Data Archive as an editor. I would say it's one of the more underused resources out there. So please use the tools that we've built. And with that, thank you to the panel members. Thank you for your insights and the doors to your worlds. And I will turn this over to Mr. Abbey and to the next panel. Thank you guys so much.
Thank you, Mike, and thank all the panel. It's a great panel.